Okay, start now. So we'll start with the motional EMF. Put a heading now. Motional EMF. Motional electromagnetic force. Motional EMF we call it. Right? Motional EMF. No, this motional EMF na. For example, listen. I want to generate a current. Basically, motional EMF is what is that here? Generation of EMF or generation of current. So we will use the rule of what is the rule I am going to follow now? I am going to follow the rule of Fleming's right hand rule. What is that here? Fleming's right hand rule I am going to use it. Why Fleming's right hand rule? Na? Listen. Because Fleming's right hand rule will give you the direction of current. Yes or no? We will actually generate what is that here? We are trying to get a induced direction of current. Okay? So direction of current will be given by whom here? Fleming's rule. Why not? Listen here. So what I'll do, for example, I'll extend my finger and I'll try to show you this rule. Okay? Like right hand, if you extend the fingers here, so let's say it is a thumb. Right? And this one is, let's say, the middle finger. And let's say this one is, what is this one here? Applied magnetic field. Alright? Or else if you are confused now, I'll take this, the index finger, this will be the middle finger. Is it okay? This is index finger and this one is a middle finger. Sorry, index finger, this is a middle finger. Can we extend like this? Yes or no? Can we extend like this? Yes or no? So now basically I wanted to show you the index finger indicates the magnetic field. What is this magnetic field? It is applied one. What is this magnetic field, buddy? It is a applied magnetic field. Right along with me? It is a applied magnetic field. Whereas this middle finger indicates what is that here? A current. What is this current? Induced current. Induced meaning? What is the meaning of induced? Which is generated current. Yes or no? So I can say it is a induced current. Induced current. Now thumb is there. What is the thumb here? Thumb indicates what is it? The speed of the conductor in the magnetic field. Yes or no? V is what is it here? Motion of the conductor, I can say. Motion of the conductor. Is it okay? Because I want to understand any EMF, first of all I should understand Fleming's rule. Right? Got it, buddy. So what are the things you have already in your hand? You will have the two things in your hand. One is magnetic field you will have. Second one is you will have a motion of the conductor. Yes or no? And you are going to generate a current here. Means any two should be there to generate other one. Are you getting my point here? It means Fleming rule is not only explains the induced current here. In upcoming days you will also understand if I have any two quantities, other quantity can be generated. Are you getting? For example, I have magnetic field, I have a current. Can I generate a motion of the conductor? Yes, of course. That is how a fan will work. If I have a current and magnetic field, I can generate motion also. If I have motion of the conductor, and if I have a current, I can generate magnetic field also. Clear? Huh? So any two if you have, other you can actually generate. Clear? Is it okay now? Shall I move on now? Right. Now we'll go with the basic formula. Shall I start next? Right. Now motional EMF, actual concept will try to do it. I am erasing all the ink from the slide. Shall I? Now let's imagine yourself. what I am doing is, so there is a applied magnetic field is there, like this. There is a applied magnetic field like this. Are you getting my point here? Magnetic field. Now what are you using here? You are using one of the conductor, and this conductor is moving. So let's say this is a conductor. Of length is how much of this one conductor length is how much I am taking? Write down L. And this is moving which direction here? Let's imagine it is moving in a this direction with velocity v. What happens first? Tell me. You use the, see, right hand rule. Can I use this one? Drawing towards it like this. Current direction, which direction then? Current direction we don't know. Magnetic field is what is that here? This index finger, right? And motion of the conductor is like this, and the middle finger is upside. Means current is actually going from down to up. Yes or no? Which means here we have a positive potential. Here what is it? We have negative potential. So automatically current will be moving or not. Yes or no? Are you getting my point? That's how it will be there or not. Are you clear? Any difficulty here? No. So now what I will do now? So here simple logic. You are moving in this direction. This is positive. Here I am trying to write a V positive and a V negative are the potential developed at the ends of the conductor. At where buddy? At the ends of the conductor. It is developed or not? Next, one more point I will write here. What is that point I can write here? So simple here. Now EMF. Just draw this figure fast. Did you draw it? Shall I move? So what is it now? At a equilibrium position, because potential is developed or not, automatically electric field also developed. So at equilibrium position, magnetic force is equal to electrostatic force. What can I write here? Magnetic force is equal to electrostatic force. Magnetic force is nothing but you know already formula QVB. So no? And electrostatic force is nothing but what is it here? Q into, tell me, Q into electric field. Can I write like that? So Q and Q can I cancel? So E is equal to what is it here? V into B. I can write this. This is my equation 1. Then the second equation, induced EMF. Induced EMF E is equal to, you know that, electric field into length of the conductor. Yes or no? So electric field we have here as a V into B, or we can use it as BLV. What is the induced EMF formula now? Can you tell me what is the formula now? BLV. Okay, that is your second equation. Julian, give me pen. Yeah. So did you understand it? Any difficulty? What is the formula? E is equal to BLV. Right now? Shall I move on now? Now you see this, because this is similar to this particular formula. Positive terminal to negative terminal it is going up. So this conductor moving will behave as a battery or not? Can I write like that? Because battery will have this is a smaller terminal, this is a positive terminal. Can I write like that? So this conductor will behave as what is it here? SL. Clear? Why? Because this is negative terminal, this will be positive terminal. So how much EMF you are generating here? That is BLV only, no? So throughout this conductor, how much EMF you are generating here? BLV. Is it okay? Understood or not? So now if the conductor is moving in a magnetic field, automatically that conductor will behave as what is it here? A cell, like a cell it will behave. So at the terminal of this one, automatically EMF will be generated. I hope you understood. Clear? Any difficulty? No. Note down. Is it clear, buddy? Shall I move on? One second. Did you understand or not? Now, what I'll do, no? Next, for example, I am thinking that for this conductor, are you getting my point, buddy? What are we trying to do? Our point is, we are going to generate a current, electrical current. Now, to this ends, I am connecting what is it here? One of the resistance we will connect. Can I connect like this? With the resistance, it is moving now. Then, what I am going to write is here, so induced current. What I will get it here? Induced current. Induced current is equal to I is equal to what can I write here? Tell me. Induced EMF divided by resistance. So what is the formula now? Tell me. BLV divided by R. Note down along with me first. Done, buddy? Any difficulty? No. Next, for example, here magnetic force also can I find? So if the conductor moving in a magnetic field, which is a magnetic field going in, then magnetic force, what is a magnetic force? Magnetic force will be, what is it here? You have studied as a Bill sin theta, right? So here F is equal to BIL. Right now they are all perpendicular to each other. Yes or no? So BIL we have it here. So F is equal to what is it here? Instead of I, what can I write here? BLV divided by R can I write it? Into L can I mention? So your formula will be converted into which format? F is equals to B square L square V divided by R. That is your magnetic force whenever the conductor is moving into the in a magnetic field. Okay? Chalo note down. Then Shall I change the slide now? Okay. Harini, I am here. Screen is there. Which direction you are watching? Why are you planning to kidnap us? They are kids, buddy. Okay. Are you watching the borders? No, right? Chalo. Shall I move forward? This lady is there. Next, write down power dissipated in a moving a conductor. Power dissipated dissipated. Okay. Writing wrong spellings. In moving a conductor. Power dissipated in moving a conductor, right? So just now we are moving a conductor, right? So obviously power will be dissipated or not. So I'll tell you something here. So if in case if conductor is moved linearly, son, we are doing linear only, no? Linearly with velocity v, a small work done will be there. Yes or no? External work is done. Yes or no? So what will I write? Power mechanical, if I write power mechanical is equals to, what is it here? Power external. Yes or no? Because it has to do externally, right? So which is nothing but a change in work done by change in a time. Can I write like that? Change in work done by change in time. So work done means what is that here? F external, external work you have to do it. F external, and because force is nothing but a work done is nothing but force into displacement. So how much external work you are doing to displace some x distance divided by t, which is nothing but F external into V. Now this F external is equal to what is that here? Magnetic force, which is nothing but what is that here? Magnetic force into V. So total formula will be equal to power dissipated is equal to what is that here? F magnetic we already had it. What is that here? B square L square V divided by R. Yes or no? So which is into V. So total answer will be what is that here? B square L square V square divided by R. That would be your power dissipated. Okay? Noted? So this is also equal to thermal power also we can call it. Power dissipated across the resistor. Same one. Noted? So till this much, so it's okay for the anxiety level, but we'll go a little bit beyond it, right? Yes or no? So we'll discuss special cases. Do you understand it? what is it? We are taking the conductor and just we are dragging across a magnetic field. Through the magnetic field, then we are generating what is it here? Electrical current or induced EMF we are generating, right? Now we will do the special cases. Right or no? Special cases. Special cases, right? So what is the special case here? First case I am trying to do that there is a magnetic field, right? So I am trying to do the magnetic field direction is in this manner. The magnetic field is applied in this manner, right? Magnetic field is applied in this manner. So now the magnet whatever you are bringing, that magnet is sorry, not a magnet buddy, I am very sorry. This is a conductor of length how much here? L length. The conductor of L length. You are moving with the velocity in this direction with a v velocity. Yes or no? Are you getting my point here? The magnetic field direction is what is it here? This is a magnetic field. And the conductor you are moving with a little angle, some angle you are making, right? So can I divide them? Can I divide them or not? I am dividing them. So because it is coming in this manner, I can divide the velocity like this. So this is theta. So this will be v cos theta, and this will be what is it here? V sin theta. V cos theta and V sin theta. Then also will generate a induced EMF. Right? Is it clear? So we will try to see both the cases. Is it okay then? So I will try to say, for example, induced EMF. Induced EMF. Okay. Let's say here x-axis, y-axis. Let's say this is a x-axis. This is your y-axis. Okay. This is negative y. According to the reference frame, we'll try to take. So induced EMF will be what is it? Tell me then. Induced EMF along x-axis. What is induced EMF along x-axis? This is induced EMF, right? So induced EMF along the x-axis na E along Ex, which is equal to B length of it L, and what is the velocity now? Which is along the x-axis. Yes or no? Along x-axis, what is it here? Ex is equal to BL V sin theta. Are you getting it clear? Next, one more step I would like to write. Induced EMF along y-axis, and here I can say very clearly B is perpendicular to what is it here? Bx. It should be very clear. Yes or no? Next case, what is it here? B is parallel to what is it here? By. Yes or no? So that time induced EMF will be what is it here? That time what happens here? Induced EMF will be 0. They should be perpendicular. Yes or no? According to the Framing's law, the magnetic field is, if the magnetic field is like this now, so let me just try to draw here. So if the magnetic field is like this now, automatically velocity should be perpendicular to this is a Vx component. Yes or no? So current will be generated or not? Which direction current will generate? Tell me. Show me here. Thumb is a conductor movement, and then magnetic field is actually downside. So current will be generated or not? Which direction it will generate? Towards us it is generated. So I can draw that current will be generated inside this one is like this. I cannot show that. Yes or no? That direction I cannot show. It is going, coming out of us. Yes or no? Like this. Sorry. Magnetic field is which is downside. conductor is towards you. So it is coming out of the plane. Current is, what is the direction of current now? Coming out of the plane. So your induced EMF will be, what is the total induced EMF will be, what is it here? E net value will be this one only. Any difficulty now? No done. Did you finish it? Is it clear? Here one point you can add up. No current will be induced. No induced then. Is it clear? Gangadhar, but any emergency? Harish, keep the scale down, right? That is not for play, that is for measurement. Vikarshini, what happened, beta? Not feeling well. Morning, what is the tiffin? Idli or dosa? Idli. Idli means you are taking alcohol into it. Shall I? Yes or no? Idli has a natural alcohol. That's why people will feel. See his face. Huh? Mabbu. Waste fellow. Shall we move on? Okay. Next special case. Next. Same sort of a diagram I'll try to draw. Okay. But here velocity is not. Let me take this separate slide. Confused. Chalo. Where is the slide? Right? Okay. Right. Case 2. Now there is a magnetic field in the same manner. Let's imagine ourselves. The magnetic field is like this only. The orientation of magnet was little bit tilted like this. Not magnet again. This is a conductor. Sorry. Okay. The length of the conductor is, what is this here? Length is actually L. This is been moving with the velocity exactly perpendicular to it with the V. Velocity is not at all changing now. Then what is the answer now? Magnetic field. So here in this case, length will be changing its value. Yes or no? Length will be, what is that here? So EMF is equal to, we will have a magnetic field is same only, but length I will take it as L sine theta. What is that here? Magnetic field will be L sine theta into, what is that here? Into V. Again the formula will be converted into what is it here? BLV sin theta. Clear? Next, one small miscellaneous concept we will try to discuss here. Okay, which may be little bit advanced level only, but easy only. It is also easy. What is Ashna? The magnetic field is like this. The magnetic field is like this. Right? The length of the conductor is miscellaneous. Miscellaneous means it can be any format, any shape. Like this, it is a curve shape like this. Okay, and but it is moving with a velocity v in this manner. Magnetic field is like this. So what will take it here? We'll take only displacement. What will take it here? Displacement. So EMF is equal to B into length effective. What is this one here? Length effective will take it. Which means effective length will be what is it? If it is the curve na diameter. Yes or no? So effective length into and into velocity v. Clear? Chalo note. Yeah, actually stand up. Stand and write. Done? Go drink a water and come. Shall we start? We finish like this part. We do one question. One JE question we'll try to do. Okay. The same model can be asked in NEET also. Shall I do this? Note on this question. Fast. Sit buddy, sit up. Did you draw it? So what is the gist of the question? Whatever we learned, same model only, no? So the loop ABCD is moving with a velocity v towards the right. The magnetic field was given 40 Tesla. The loop connected across the resistance is also given. If the steady current at 2 amperes flows in the loop, then value of V in the loop has a resistance of 4 ohms will be. Then, okay, chalo. Now if it is 37, this is little bit tilted length, right? Am I correct? The length is, what is this here? Tilted length. So we'll actually resolve the length like this. Am I correct? So this direction, what is this one here? This direction L, what is this? L cos alpha, sorry, L cos 37. What about this one here? L sin 37. Am I correct? L sin 37. We got it now. This is L cos 37, L sin 37. Right? Now it is been moving with the v velocity. Right? So now, what is it they are saying? The moving with the velocity v towards the right. The magnetic field is 40. The loop is connected to resistance of how much here? 8 ohms. How much you are connected here? 8 ohms. So first we will try to solve with that 8 ohms. Okay. So we will try to do right side with the connected resistance ohm. If a steady current 2 amperes flows in the loop, then the value of V, if the loop has a resistance, is how much here? 4 ohm. Should I connect with the 8 ohms or 4 ohms? See, logic you should understand. This loop, if complete loop is how much here? This complete loop is how much? 4 ohms. Mean complete loop is how much here? 4 ohms. Already we have how many ohms here? 8 ohms. Total R equivalent value will be how much? Tell me. They are in series only, no? So 4 plus 8, it will be total how much here? 12 ohms. Clear? You should be very careful. The loop itself has how many ohms here? 4 ohms. Externally 8 ohms. Totally how much here? 12 ohms. Clear? Now we know already current I is equal to induced EMF divided by R equivalent. Induced EMF is nothing but we have it as a V L effective is a no into V divided by R equivalent. Can I use it like that? So now we have it as I into R equivalent, right? Which is equal to what is it here? V L effective. Effective means what is it here? L sin 37 degrees into V, right? Remember one triangle I will try to tell you. This is the triangle, right? This is a triangle where you have a 37 degrees here. So what about here? 53. What about here? 90 degrees. Yes or no? So sin 37 is always 3 by 5. 3 by 5. It is 3. This is 5. This should be what is it here? 4. Clear? Sin for 53 will be how much here? 4 by 5. Yes or no? You might have studied this one in math already. Use this thing and find the V value. Do it. So I value is already 2 amperes, resistance is 12, B value is 4, L value is how much here? Length, did they mention length? AD, they have mentioned already, AD will be 30 centimeter. 30 na, you will write it as in terms of meters, 10 power minus 2. Yes or no? This is nothing but what is this? AD only. L is nothing but what is it here? L is nothing but a AD only. Then sin 37 is how much I told you? 3 divided by 5 and we have it as V. Now calculate. So if 5 comes this one, 10 into 12 is equals to 4 into 30 into 3 into 10 power minus 2 into V. Now what happens here? 4 threes are 3 3 will cancel. 110 is also cancels here. Yes or no? So V is equal to what is that here? Yes or no? V is equal to 3 divided by 10 power minus 2 or else 100 divided by 3. 100 divided by 3 will be how much, right? Ah, very good. 33.33 like that. Volt will be the correct answer. Right? You understood? You completed, na? Thank you. Leave. See you in the next class. So next class is sixth class, right? Chalo. Thank you. Move. Slowly move out of the hall. But you switch off the lights, that's it. Completely. Yeah. Harish, leave the hall. Yeah, buddy.